live long enough to get the Nobel Prize, but you actually have to live long enough to see the fruit of your experiment. So this is, and now you see a lot of detail, and in fact, it's amazing. Now, in fact, cosmology has been brought back into the realm of astrophysics, because in fact, one can use all of this data to determine to measure the multipole expansion of this noise spectra, and then you can then compare that with what inflationary models of the universe predict, and the comparison is remarkably good. So these are the architects of the COBE satellite: John Mather, who is at Goddard Space Flight Center, and George Smoot, who is at Lawrence Berkeley National Laboratory, which is kind of loosely attached to that other university on the other side of San Francisco Bay, UC Berkeley. Stanford people don't like to mention that, though. Anyway, so they won the 2006 Nobel Prize for this work, which is really, I think, a very welcome prize. Anyway, so now I come to the second of my three topics for discussion, and that is the process of advancing science often leads to inventions and technologies that directly benefit mankind. However, it is impossible to know from where an advance will come that might solve a problem facing mankind. And I will use just one example to illustrate this, and that is nuclear magnetic resonance. And the backdrop here, how many people recognize what this is? Not very many. This is part of the Iguazu Falls. And there was a lot of water. There are two levels at this point. This was taken from the Brazilian side. Anyway, it's a spectacular place to visit. So NMR was developed just 1 year after the end of World War II in 1946 by these two gentlemen, Felix Bloch at Stanford University and Ed Purcell at Harvard University. Just 6 years later, they were awarded the Nobel Prize for their work. Now, they had invented NMR to study the distribution of electric charge within the nuclei of atoms. So, in fact, in 1952, they got the Nobel Prize for their development of new methods for nuclear magnetic precision measurements and discoveries in connection therewith. And look, I know exactly what happened to these guys because it happened to me too. You go to Stockholm to get the prize, and then there are all these reporters, and they ask you to explain what it is that you've discovered. And well, it's hard to do that, particularly if these guys are not scientists, which by and large they're not. And so after a few minutes of stammering, they will interrupt and say, well, what do you think this might be good for mankind? And they did that for me with superfluid helium-3, which only exists within a couple thousandths of a degree of absolute zero. So anyway, I've never seen this written down, but there are plenty of people at Stanford that knew Felix Bloch. And Felix Bloch, when asked what NMR might be good for, said, damn little. Felix was, I guess, a little bit of a curmudgeon, and he felt that you shouldn't expect benefit to mankind when they had done all this wonderful work in studying the distribution of charge in atomic nuclei. Ed Purcell at Harvard was a slightly more thoughtful person, and he suggested that one might use NMR to calibrate magnetic fields. And in fact, you can do that. But let's see what NMR has actually been used for over the years. So eventually people were able to create very homogeneous magnetic fields. And when you did that and you looked at the protons in some organic solvent that was generally either a pure form or in solution, what you found was that not all the protons resonated at exactly the same frequency. Now, if you wanted, people are sitting there saying, what on earth is NMR? So think about a simple gyroscope. If you take a gyroscope that has angular momentum in one direction and you tip this guy sideways, then gravity is pulling it downward and it tends to precess. And that precession is exactly what happens to atomic nuclei because they have a magnetic moment, and if you put them in a magnetic field, they want to line up parallel to that magnetic field. But if In NMR, you tip them away from that magnetic field and they precess. And the precession rate is governed by the strength of the magnetic field, the strength of the dipole moment, and the angular momentum of the nucleus. And so this basically gave you a lot of interesting information. But here you're finding, in fact, that not all the protons resonate at the same frequency. And it soon became clear that, in fact, these were due to chemical and spin shifts in these organic materials. And at this point, NMR became an essential tool of organic chemists all over the world. And still to this day, if you go into an organic chemistry laboratory, you're very likely to find an NMR spectrometer. So but early on, NMR was all done by slowly sweeping either the magnetic field or sweeping the frequency, and it was very difficult to get the spectrum. It took a long time. Richard Ernst then, who grew up in Switzerland, came to Palo Alto, started working at Varian Brothers, and when he did that, he was able to, in fact, I would say, port Fourier transform spectroscopy. This is now a technique where you now tip all of the spins, and they all are processing at different frequencies, and you do a Fourier transform of that signal that you recorded, and that basically gives you the NMR frequencies of all of these atoms, Fourier transform spectroscopy. And then using that, Richard Ernst and Kurt Wutrecht were able to do what they called two-dimensional NMR. So they would apply a pulse and tip one of these spins, and then they would look how, in fact, tipping this spin basically took it out of the picture, and then they would measure the resonant frequency, how the resonant frequency on an adjacent spin changed. And that allowed them to determine information about bond lengths, which is independent of all the other techniques that existed at that time. And so in 1991, Richard Ernst, who, by the way, I met this summer, he was at a very interesting Asian science camp for students on the island of Bali, and that's why I had that picture from Bali. Anyway, so Richard Ernst here is smiling, and he was given the Nobel Prize for Chemistry in 1991. But actually, if you go back and look at this work, two-dimensional MRI, was really done in collaboration between Richard Ernst and Kurt Wutrecht. And Kurt Wutrecht was very interested in not just determining bond lengths, but actually determining the entire structure of organic molecules. And he succeeded in doing that. This is, in fact, the bovine pancreatic trypsin inhibitor, is a small protein, and in fact this structure is known with remarkable detail in solution, whereas the only other way of determining the structure of a protein was to crystallize it and then do X-ray crystallography. A very complicated process, and it wasn't very clear that the structure would be exactly the same in crystalline form as it would be in solution. And so, in 2002, 11 years after Richard Ernst was given his Nobel Prize in Chemistry, here's Kurt Wutrecht, and you can see he's smiling as he accepts the Nobel Prize from King Carl Gustaf of Sweden. So, but we're not done, because going back many years to roughly 1972, people began to realize that if you applied a magnetic field gradient across your sample, that as the spins precessed, the frequency that they precessed at would have encoded in it positional information about where that spin was coming from. And then if you applied magnetic field gradients successively in 3 different directions, in fact, you actually could obtain images such as this. This is an image of a healthy human knee, and I know the difference. Neither one of my knees is very healthy anymore. So the medial meniscus is missing from one of my knees, and in fact, so is well, it doesn't show on here, but the anterior cruciate ligament is also